Okay, so let's talk a little electromagnetic induction. The basics of this, of course, you all would have met it in Form 5, but the discussion or the explanations aren't going to be much different, but of course we still go through all of it, right? Now I have on the right hand side some very basic equipment used to demonstrate electromagnetic induction. All you really need is a magnetic field and a conductor, basically, that is sufficient for you to generate it here. So what I have, of course, is this is a bar magnet itself. Good. And this itself here, you can't see it very clear in this picture, to tell you the truth. This here is a coil of wire, right? A coil of wire, not a solenoid. The difference, but the major difference between what they call a coil of wire and what they call a solenoid is a solenoid, the, how to say, the cross-sectional area is small when you compare it with the length of the solenoid itself. So this is, yes, it is a coil of wire. Yes, it has a certain length and whatever it is, but I mean, it is, that length is very small when you compare it with the cross-sectional area of the coil itself, right? Anyway, so a coil of wire, and then of course you have your, well, I mean, you kind of see in it here, galvanometer, right? Right, there's your galvanometer there. Now, of course, the purpose of the galvanometer is to detect if a current flows. Well, the current flow will be, of course, in the coils of the coil of wire itself, through these conducting leads and into the galvanometer itself, right? Now, you do not need to have a closed current path in order for electromagnetic induction to take place, right? At its very, well, at its most fundamental stage, what is actually induced is an EMF is induced, not really a current, right? The EMF could cause a flow of current if there's a closed circuit path within which the current could flow. So what is actually generated is an EMF, right? Now we speak a lot about induced current because, in, you know, to observe the EMF you need to have some kind of closed circuit path itself. If you want to observe the EMF, you would have to replace EMF itself, as in the voltage that appears. You would have to replace this galvanometer with a very sensitive voltmeter, right? Of course, a galvanometer is extremely sensitive. I'll show you all a video in a little bit where they have a center zero galvanometer that detects, well, up to 50 microamps, right? Which is an extremely small current itself. Good. Now, you could carry on this experiment in a number of ways. You could move the bar magnet in and out of the coil. You could move the bar magnet on the side of the coil up and down like this here, back and forth like that, or you could move it in this direction itself. Now, once there is any kind of relative motion, now we are speaking about moving the bar magnet, we could also move the coil itself, right? Now, the important thing is that there is some kind of relative motion between your conductor and the magnetic field itself, right? So let's first of all say that if they ask you to describe what is the concept, or the, you know, in a few words, in your own words, describe what is electromagnetic induction. This is the creation of an EMF across a conductor whenever there is changing flux linkage with the conductor, right? With the conductor itself, right? Now, there is a direct link between, of course, flux, magnetic flux, and magnetic flux density, right? So we already met this equation here, that magnetic flux phi is related to magnetic flux density. Phi is equal to BE itself, right? So sometimes in our description, we speak about changing magnetic flux density, right? Talking about changing magnetic flux density is equivalent to talking about changing magnetic flux itself, right? The only measure that connects them is the area, right? Now, in this experiment here, the area they are talking about in the coil of wire experiment, the area they are talking about is the area inside of the coil itself. That's the area they are talking about, right? Now, once the magnetic flux or magnetic flux density changes with respect to this area here, you would have induced in the coil and, well, a current itself, because if the coil is connected in such a way that a current could flow, right? Or you could have an induced EMF. That's the more basic thing that happens, right? Now, in terms of the coil itself, if you have a coil of wire, let's see, right? Now you have a coil of wire. Here, kind of trying to draw it with a kind of 3D looking effect anyway. Now, when you have your bar magnet, right, and this is mentioned in the video itself, right? Now, a bar magnet does not have a uniform magnetic field, at least on its exterior, right? The magnetic field lines go outward. Well, it actually goes outward from north, and so on and so on and so on, right? So this is the magnetic field pattern of a bar magnet over there, right? Now, when you move the bar magnet with respect to the coil, or you move the coil with respect to the bar magnet, right? Because this is a non-uniform field, you will always be changing the flux density in the presence of the coil from being either you are moving it from high flux density to low flux density itself. Now remember we said that flux density is visualized by the closeness of the magnetic field lines. So closer to the magnet, you have greater magnetic flux density than further away. So if this is your coil over here, and you move the magnet towards the coil, right, you are moving it in such a way that this north pole is approaching the coil itself, right? And closer to the north pole, the field lines are closer together, so you have greater magnetic flux density closer to the coil itself, closer to the magnet itself. So in that way now, you are moving the magnet in such a way that the flux density in the region of the coil of wire is going from low flux density to a higher flux density if you move the north pole towards that direction like that. So you are increasing the flux linkage with the coil in that case by increasing the magnetic flux density, right? Now, of course, if you draw the north pole away from the coil itself, in that way now you would be going from, or changing the flux density such that you are going from having a higher flux density in the region of the coil to a lower flux density in the region of the coil. That is what happens when you move the north pole away, right? Now, in both cases there, the flux changes in the region of the coil, or you would say now, I'm sorry, the flux density changes. So therefore, the magnetic flux that is linking the coil changes, right? Now, you could change the linkage of the flux in a variety of ways, right? You could move, as we are talking about here, you could move the magnet with respect to the coil, but I'm sorry, you could have the coil stationary and move the magnet, or you could keep the magnet stationary and move the coil, right? Another thing you could actually do is you could have a magnetic field that changes with time. It's not that the field is moving. It's not that what is creating the field is moving. But let's say you have a field that is being created by let's say a solenoid. A solenoid connected to let's say an alternating source, right? Remember, an alternating is where the current travels in one direction during one period of time and in an opposite direction in another period of time, right? The details of AC is actually done in module 2. Anyway, so this is a case where you would have a changing magnetic flux density of this solenoid here if you have an alternating source. So if you keep your coil of wire close to the solenoid, you could put the solenoid inside of the coil of wire or whatever it is, or you could, if your coil is small enough, the coil itself could go inside of the solenoid, whatever it is, in the vicinity of the solenoid, right? You would probably want to put the coil inside of the solenoid because the flux density of the solenoid is greatest inside of the solenoid itself, and the computation of it is actually that mu naught Ni that we learned before is for inside the solenoid, not the outside. Anyway, so in that case now, the coil and solenoid are not moving with respect to each other, right? But what is changing now is the flux density, so the flux linkage will change with time, right? So you could move the, so let's just mention that very quickly. So flux linkage can change in a number of ways. You could move the magnetic field, right? For example, moving the magnet in that case there with the coil or whatever conductor stationary. You could move the conductor itself. You could move, you could have a changing magnetic flux density, right? And you could also have, well, I didn't mention this before, you could have a conductor that deforms. So you could have a deforming conductor, right? A conductor that actually changes shape with time, right? So for example, if you take a wire and you put it in a uniform magnetic field, you bending the wire alone is sufficient for you to produce an EMF, right? Now, something that is mentioned in the original statement I make there, right, and it is assertive in its language, whenever there is a change, there is changing flux linkage. So electromagnetic induction is not a before and after thing, right? The EMF is induced while the flux is changing. So if the flux changes and then, attains some kind of constancy, then once it stops changing, there is no induced EMF. So so EMF is not induced when the flux has changed, but rather while the flux is changing itself, right? Anyway, now before we look at that video itself, I want to talk about Faraday's law, right? We'll mention this. Well, I want to get back to this diagram here after a little while. You just add a little page in between here, and I'll get back to that diagram itself. Yeah. I don't need to display this as a matter of fact. Right? Now, Faraday's law, right? Basically quantifies to some extent, or allows us to be able to quantify the EMF, the magnitude of the EMF that is generated. So Faraday's law says you all should have met this in Form 5, the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux density so the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux density linking the conductor. I just want to take out a word that doesn't belong there. Is directly proportional to the rate of change of magnetic flux linking the conductor with respect to time. Right? The actual equation itself, we'll discuss it afterwards, right? Now, so that gives us the magnitude. Now, the direction of the EMF, right, or the polarity of the EMF, if you prefer, that could be verified experimentally, right? Now, I have on the right-hand side here a little graphic that helps us to understand how the EMF itself is going to be created, right? Now take for example, well, it's four separate diagrams here, right? If I look at the first diagram there, I have a solenoid, not really a coil of wire, let's say a solenoid, right? And in this solenoid here, now the solenoid, no EMF is induced on, no EMF is being supplied to this coil itself, right? There is a load connected to it and whatever. I guess they want it to be, physically, in a physics sense, they want it to be accurate with their description, right? So, I mean, if you just have the coil short circuited with no load connected to it, it means that as soon as you would be generating a current in the coil there. That's how to say, that will flow without any hindrance in the coil itself, which will heat up the coil and so on and so on. So they didn't want to have a short circuited coil is basically why they do that, but that is not a necessary part of the diagram. Anyway, so experimentally speaking, when I push a north pole into this or closer to this particular solenoid there, an EMF is generated, or induced, I should say. And because I have a closed current path, now a current flows. So there's an induced current, right? Now, when you have a current flowing in a solenoid, that constitutes or that creates a magnetic field of the solenoid itself. So this changing flux here, due to this external magnetic field, eventually creates a magnetic field, right? An induced magnetic field. So the induced EMF produces an induced current, and the induced current produces an induced magnetic field, right? Now, if you use the right-hand grip rule on that solenoid itself, there we curl our fingers, right hand of our right hand, of course, curl our fingers around the coil. Your thumb will point in the direction of the north pole of the solenoid, right? Or give you the direction of the magnetic field inside of the solenoid. So you're pushing a north pole towards this this coil here and creating an induced north pole there. Now, that north pole, of course, you are trying to bring two north poles together, you will experience repulsion, right? So what is created by the motion of that north pole towards the solenoid? It actually opposes what was creating it in the first place. Now, that there is a consequence of the principle of conservation of energy, right? Now, I could explain why, using energy considerations, why it cannot be a south pole. It has to be a north pole created in that situation. Now, if you think about this, right? The current, in this case here, flowing through that resistor there, basically represents electrical power or electrical energy being dissipated, right? Now, so, and basically, electrical energy shows up in the solenoid, right? Now, if it were a south pole there, right, then it means now that the current flowing in the coil there would then produce a magnetic field that attracts the magnet that I am pushing towards the coil itself, right? Now, the work input, first of all, before I even get into all of that, the work input is the work I do in moving the magnet itself. So that is the energy that is put into this system, right? Now, if it was a south pole created, you could think about this here. If it was a south pole created, right, it means now that there's a magnetic field that is now capable of drawing the magnet towards the coil, right? So my initial input of energy now, if it created a south pole, creates a situation, hypothetically speaking, where I don't need to put in any energy again, because if this created magnetic field is pulling the magnet towards the coil, I don't have to put in any work, right? So what happens there, the work that I put in to start the process now, it then just it multiplies. Because once I put in that work and a current flows in the circuit itself, that there is my energy that shows up in the system, right? But if now that energy I put into the system is capable of doing work on the impetus that created the energy in the coil itself, but that doesn't make sense. So it means now that I could just let go of this magnet the coil will draw the magnet into itself. So, but the only way the coil could draw the magnet into itself is if electrical energy is put into the coil. So, where does that energy come from if the current would continue to flow, right? It doesn't make sense, right? So, for you to create a south pole there, it it means now that there is some sort of, or there is something wrong with the energy considerations in that system if it were a south pole created there, right? So the energy that I put in, it shows up as the electrical energy in the charges flowing in the coil itself, right? And of course, because now the only energy that I put in, sorry, only the energy that I use or the work I do to move the magnet towards the coil, only that energy could show up in the coil itself. So it has to be a north pole showing up there. Because as per my discussion I just made there, a south pole would then reveal some sort of energy being created out of nowhere kind of thing, right? So the formation of a magnetic field that basically opposes the magnetic field that causes that that other magnetic field, there is a consequence of the principle of conservation of energy, right? Now Lenz's law explains now how your induced EMF will show up, basically the polarity of the induced EMF, right? And it comes out of a discussion of the action of the induced magnetic field on the change in the magnetic flux that created that field in the first place, right? So this is Lenz's law. So Lenz's law says that the EMF is induced such that it opposes the change in flux linkage. Right? Quite simply, that is what Lenz's law say, right? So your EMF, if you ever required to check for your polarity of your EMF, it will always be induced in such a way that it will oppose the change in flux linkage that caused it to exist in the first place, right? Now, Lenz's law mentions flux linkage and not flux density, right? But remember again, there is a very straightforward relationship between flux linkage and magnetic flux density. Okay, so to talk about one is to talk about the other in this particular situation here, right? Now, just to mention something a little bit obscure that they could ask you about, right? Is it possible to move the conductor in such a way that you don't, well, in the presence of a magnetic field, is it possible that you could induce no EMF? It is possible. If you move the conductor in such a way that you do not cut any field lines, that is, you do not change the flux that is linking the conductor, and that in that situation you would not be inducing any EMF across the conductor itself, right? So let's say, for example, I have a magnetic field that is in the plane of the page, or these field lines, I should say, are in the plane of the page, or the magnetic field, sorry, uniform magnetic field, the field lines are parallel to that surface there, right? Good. Now, if I take a conductor now and I move it in that same direction, so I move it with the field lines, then I am not cutting any magnetic field lines there. I am not intercepting. I am not changing any linkage of flux with that conductor there, right? So in that case now, I am moving in the presence of a magnetic field, but I am not moving in such a way that I change the flux linkage. Flux linkage only changes when you cut magnetic field lines, right? I will show you all that little clip there now because it gives you a little view on the actual equipment and so on, and different ways you could vary the amount of induced EMF that shows up and so on, right?
these two videos, I was moving a magnet into and out of the center of a coil to generate a current in the coil. A viewer inquired as to what would happen if I moved the magnet laterally to or along the outside of the coil. This video demonstrates and explains what happens. Here is a bar magnet with a north and south pole. Running inside the magnet will be lines of magnetic flux density field, which will then emanate outside the magnet. Here is an illustration of those lines of magnetic flux density. So they'll emanate out the north pole and around the magnet and then back in the south pole. And you can see that the spacing between the magnetic flux density field lines will decrease as you move away from the magnet, indicating a reduction in strength of the magnetic flux density field. Here I have a galvanometer and I have it connected to a 100-turn coil. So whenever there's a changing magnetic flux with respect to time inside the coil, there will be an electric field generated, and that electric field inside the coil will result in a current flow. So when I take this bar magnet and move it towards the coil, there's an increase in magnetic flux with respect to time, and I see a positive current generated. Now when I remove the magnet, there's a decrease in magnetic flux with respect to time, so I have a current flowing in the opposite direction. And the current that's generated is proportional to the rate of change of magnetic flux with respect to time. So I move the magnet slow, I get a small current. If I move it fast, I get a larger current flowing. I was asked the question, what would happen if instead of moving the magnet into and out of the coil, I was instead moving it around outside the coil? Well, as long as I'm moving the magnet, I am getting a change in magnetic flux with respect to time inside the coil. It's just that that change in magnetic flux with respect to time will be small because the magnetic flux density field falls off with distance from the magnet. But if you watch closely, when I'm moving it lateral to the coil, you can see a little bit of movement of the needle indicating I am generating some current. Similarly, if I'm moving it alongside the coil like this, again, I'm getting some change in magnetic flux with respect to time, and you can see a little bit of movement of that needle indicating a little bit of current being generated. Now the current generated is going to be proportional to the change in flux linkage with respect to time, which is the product of the change in magnetic flux inside the coil and the number of turns of the coil. So if I greatly increase the number of turns of the coil, then when I move the magnet outside the coil, I should be able to generate much more current. So here's a coil I wound that consists of 30,000 turns. So for the same changing magnetic flux inside the coil here, I'm going to get a much greater change in flux linkage. So let me now connect this 30,000 turn coil to the galvanometer. So now even when I move the magnet slowly, I generate current because of the large change in flux linkage with respect to time. So I have to be careful not to move it too fast and damage my galvanometer. Okay, so now let me move the magnet laterally. So you see there was a current generated because there was a changing magnetic flux inside the coil. So as I'm moving it towards the coil, there's an increase in magnetic flux, and I was generating a positive current. Now, as I continue to move the magnet and away from the coil, now there's a decrease in magnetic flux inside the coil and a negative current generated. So now I'm going to take the magnet and move it alongside the coil. So as I'm moving it towards the coil, I noticed I was generating a positive current, and as it continues to move away, now it's a negative current. So as I'm moving it towards the coil, I'm generating an increase in magnetic flux and a positive current flow. And now as it's moving away, I have a decrease in magnetic flux and hence a current flowing in the opposite direction.
Right. So I hope that would have, well, I mean, the purpose of it was to demonstrate the fact that, well, if you were observing, looking closely at the video itself, you would notice that only when the magnet is moving there with respect to the coil, or only when there's some relative motion um, between the coil and the bar magnet itself, was there any deflection observed on the galvanometer itself, right? So moving a north pole towards it, moving a north pole away from it has opposite effects, and you could observe that by the deflection on the galvanometer itself, right? Now there's one equation. I'm sorry, before I get to that equation itself, I just want to give you all an equation that actually is not on the syllabus, but I think it's a necessary part of studying magnetic flux density and flux linkage and changing flux linkage, producing an induced EMF and so on, right? So we have these two laws here, Faraday's law and Lenz's law, which basically collectively describe, or you could use them to quantify both the magnitude and direction of the induced EMF itself, right? So the two laws collectively, the law is actually called Faraday's law, but there's a part of it that is borrowed from Lenz's theory itself. So it says that the induced EMF E here is negative of the change in magnetic flux density divided by the time you are talking about, right? Now the change in flux, I said flux density, it's a change in flux linkage of the coil itself, right? So this here, as I said, this is a change in flux. This here is, of course, obviously the time interval, and so rate of change of flux with respect to time is change of flux divided by the time taken, right? So this itself comes from, this portion itself comes from Lenz's law. And then this entire thing here, change in flux divided by the time taken, that is from Faraday's law, right? That's from Faraday's law itself, right? Now, usually you don't apply the equation itself in this form with the actual negative sign and so on and so on, because what you are really interested in is just the magnitude of the induced EMF. So the magnitude, you just leave out the negative sign when you are talking about the magnitude itself. So the magnitude of the EMF, E, you just do delta phi over the time taken, right? Now, delta phi itself, remember phi is BA, right? So you have delta BA divided by delta T, time taken, common T, of course. So once this quantity BA changes, you have the generation of the EMF, and delta BA divided by delta T gives you the magnitude of the EMF induced. Now, typically what would happen is you wouldn't have a change in area, you would just have a change in magnetic flux density. So E in this case, EMF in this case, basically boils down to delta B itself multiplied by the area divided by the length of time taken most of the time. So this here could be used for a, well, sorry, I'm not going to say what, that's actually a general formula, right? Now for a coil of n turns, right, you would have to multiply the effect by the number of turns, because each loop of the coil has an area A, and each loop is experiencing that change in magnetic flux density. So for a coil of n turns, you typically have to use this formula here. In a lot of questions, it will be n delta B, change in magnetic flux density A, divided by the time taken, right? I do have a couple questions to add on where I actually apply this formula, right, itself. But there is one special case that is mentioned in the syllabus itself. And let's talk about the a straight conductor, not a current carrying conductor, just a straight conductor. Moving in a magnetic field. So a straight conductor, so consider a straight conductor of length L moving with a speed v at right angles to a uniform magnetic field flux density B, right? So what would happen there is you would have, this is your uniform magnetic field, let's say just arbitrarily into the page itself, right? So you have your straight conductor. We draw that here using this thingy here. Let's say a straight conductor is moving like that, right? So the length L I'm talking about is this length here, right? And you are moving it in this direction, so the motion is this way. So a uniform magnetic field into the page, a conductor of length L, let's say moving in that manner there, right? Now, as the conductor moves, of course, it will travel, let's say, a distance D. Let's say a distance D in this direction here, right? Now, what it actually does, of course, when it does that, or while it is doing it, I should say, or having traveled that distance D, or, you know, it happens while it's in motion. That's the important thing. Now, what would happen is it would cut the field lines. It will cut the field lines, and then that involves now linking this amount of flux here. So once you cut field lines, you know immediately that flux linkages is changing with time, right? So it is moving in that direction. So the flux linking it changes with time. And the flux that links the conductor, right, while it is moving, let's say through a distance D, because you have to observe the motion over a period of time in any case, right? So over a period of time, delta T, the wire, well, the conductor, let's say, describes an area A, right? So it's that shaded area there, which links a flux, let's say phi, right? Now, of course, phi itself, right? Let me call the change in magnetic flux linkage, because flux is linking the wire itself because it is perpendicular to it. So while it is moving, it is going to cut new field lines. So flux is being linked. So it links a flux, let's say delta phi in this case here, right? So delta phi is of course B by A itself, right? The magnetic flux density by that area it would describe, right? That imaginary area, let's see, right? Now the area itself is area, and that area is of course the length of the conductor multiplied by the distance D, that it travels in that direction of the motion there. But the distance d itself now is the speed of the conductor. The distance d is the speed multiplied by the length of time there. So over time, delta t, the conductor moves a distance d, and therefore describes an area A, which links a flux delta phi, right? So phi is BA. A is the area, of course, as I mentioned there. The area is rectangular in nature, so it is L by D. The distance traveled, of course, is the speed by the length of time taken itself, right? So delta phi in this case here, the change in magnetic flux that links that conductor is L V delta. I'm sorry, I forgot out the B there. So it's B by the area A. This is the expression for A below there. So it becomes B L V delta T. So the EMF induced will be, of course, delta phi divided by delta T. Oops. Which is, of course, BLV delta T divided by delta T. The delta T will cancel. So therefore, and I'll scroll down a little bit because I do have some space, that the EMF induced is what? The EMF induced, E is BLV, and that is a long, I'm sorry, not a long straight conductor, sorry, a straight conductor of length L moving with a speed V at right angles to a magnetic, a uniform magnetic field of flux density B. That there gives you the EMF induced in such a conductor itself, right? Now, so that's basically the theory behind induced EMF and so on. So I'm going to stop this video now. I do have some another video to add on to it where I would go through some of the questions and so on from the past papers as worked examples.